In class today, we talked about how to find the derivatives of inverse functions. And ultimately, that led us to finding formulas for the derivative of all of the inverse trig functions. And I pulled a table from your textbook. It looks very similar to this one. And I wanted to explain what this thing says if you happen to be reading the lesson so that you don't get freaked out about this notation. So just to remind you what happened in class, we end up saying that the derivative of the inverse sine function was 1 over the square root of 1 minus x squared, which is true if you're just doing the inverse sine of x. But when there's a composition involved, remember that we have to do u substitution. And so what we end up with is 1 over the square root of 1 minus u squared. And then you have to multiply by the derivative of u, which we've been calling u prime. Now, when you multiply a fraction times a whole number, if you will, remember that this is u prime is kind of like over 1. And when you multiply those together, this u prime ends up on top. And so the formula that we would use for the inverse sine of a function u would be u prime divided by the square root of 1 minus u squared. And that's what this formula says, except that they're using Leibniz notation for the u prime. So it's still 1 over square root of 1 minus u squared. It's just that the derivative gets multiplied by that 1 and stuck on the numerator. Now, the other thing that they indicate here, which is true, is this function u has to be less than 1. Otherwise, this square root bonks. So just keep that in mind, that when you're doing the square root of 1 minus u squared, the only way it works in the real numbers is if the absolute value of u is less than 1. So these formulas are all the same formulas that we came up with in class today. So you can use those. We made our own list in class, which is very similar to this one, but this is the one that comes from our textbook. And now what I'm going to do on the next slide is just run through quickly a couple of derivatives for you so that you can see how this thing works, and it's actually pretty straightforward. So here are two of the problems that we had in the assignment, number 9 and number 10. One thing we discussed in class was that sometimes in mathematics, especially when you're working with the natural log function or trig functions, we call those transcendental functions, when there's only one term that the trig function is receiving, we don't write the parentheses. But keep in mind that this is the inverse secant of 5x to the fourth, and this is the inverse tangent of 3x squared. The parentheses are there, they're implied. And so what that means for number 9 here is essentially this 5x squared, or 5x to the fourth, becomes our u. And our u prime is 20x cubed. Then the derivative of this thing is pretty straightforward. We just write y prime, the derivative of this function, is going to be 1 over the absolute value of u, which we'll fill in a minute here, times the square root of u squared minus 1. I'm copying this right off the formula that we have, times the 20x cubed, which is the u prime. That should say 20x cubed. Okay, so our final answer for this thing is going to be that y prime equals the 20x cubed will end up on top. We're going to divide by the absolute value of u, which is 5x to the fourth, square root of u squared, so 5x to the fourth squared. Be careful with that. That's 25x to the eighth. When you square 5x to the fourth, you square the 5 and you get 25. And you square x to the eighth and you multiply the exponents. Or square x to the fourth and you multiply the exponents. Minus 1. Now, there's a little bit more math we can do. I'm going to have to move down here into the black space to simplify this thing. So the absolute value of 5x to the fourth turns out to be 5x to the fourth because x to the fourth is already positive. When you raise any value of x to the fourth power, it turns positive. So there's no reason to have these absolute values. That means I can ignore these because x to the fourth is positive, and I can reduce the 5 and the 20. So the final answer, if you happen to be peeking at the answer key on this thing, is going to be 4x cubed Ooh, even better. I've got an x to the fourth on the bottom and an x cubed on top, so that's just going to be 4. And then the 5 is gone and 3 of the x's are gone, so this is x square root of 25x to the 8th minus 1. And that thing is about as simple as we can make this derivative. 4 over x times the square root of 25 times 8x, not 8x, 25x to the 8th minus 1. I don't really like how that blue is sitting in that highlighter, so I'm just going to see if I can trace over this again and make it look a little nicer. No, that doesn't look any better either. Okay, so we followed the formula. Be careful with the absolute values. Sometimes you can get rid of them, right? Actually, you can always get rid of them, but you have to be careful. Sometimes there are cases. We don't have to worry about cases here because x to the fourth is always positive. All right, let's look over here at this tangent problem. Again, because these parentheses are here, I can say u equals 3x squared and u prime equals 6x. And then as I'm writing this derivative out, it's y equals 1 over 1 plus u squared. That's the formula for inverse tangent. And then we have to multiply that by the u prime, which is 6x. And this one will be easy to fix here. This is y prime. Y prime is going to be 6x in the numerator over 1 plus 3x squared, which is 9x to the fourth. And there's no reducing we can do on that one. So this one we're done now. The inverse tangents are very common because tangent is such a useful trig ratio for solving real world problems. And so we may, from time to time, have to take the derivative of an inverse tangent function. And the other thing I like about the derivative is there's no square roots in there, which sometimes students struggle with. So these are just 2 examples to give you a little more understanding of how to write these out and how to solve and simplify. I shouldn't say solve, I should say simplify. Okay, so give a go on the rest of the problems, and then next time we see each other, you can, of course, ask me more questions if you have them. In the meantime, take care.